Good day, my dear students. In this video lecture, I will be introducing the concepts of vectors. In the first part, I will be defining what vectors are. The objectives of this video lecture are the following. At the end of the video lecture, you need to be able to differentiate between vector and scalar quantities. You also would be able to define what a resultant is and have an understanding why you need to review basic trigonometry concepts in order to solve for the resultant or solve problems involving vectors. Let's start with some definitions. Let's differentiate vectors from scalar quantities. Vector quantities requires both magnitude and direction for a complete description. Meanwhile, scalar quantities only require the magnitude for it to be described. It doesn't involve any direction. You have already encountered several vector quantities before. These include force. When you report a force of 40 Newton, for example, I also require you to include the direction. In this example, the force is 40 Newton directed to the object to the east. Displacement is also another example of vector quantities. You don't only say 6 kilometers, but you also need to include in which direction was the object displaced. Acceleration is also an example. 9.8 meter per second squared is the value of g, or the acceleration due to gravity, and it is downwards. Velocity is also another example. 50 miles per hour, and the object is going to the north. Why is it important to include the direction when describing these quantities? For example, you want to move this green box to point A rather than point B. Point A is located along the north or along the y-axis, while point B is located along the x-axis. So in order to move the green box to point A, you need a force that is directed to the north. Okay, so if you want to put your green box to point B, you need the force that is directed to the east. You need an idea in which direction you are um, pushing the object, because the result will be different depending on in which direction you push. The location of the object afterwards, after you apply the force, will be different. It all depends on where the force is acting on the object. Another example, remember, of a vector quantity is a displacement. So if you are this yellow dot in the middle of the axis or at the origin, and you want to go to point A instead of point B, what you can do is to first walk several steps to the east, and then afterwards make a left turn and walk several steps to the north. That's how you're going to get to point A. If you want to get to point B, you would walk to the east and then to the south. So direction really matters when describing vector quantities. Another example is acceleration. So if this is a car, for example, and it is moving, but you want the car to stop at point A, you have to decelerate or to slow down to the right so that you can stop at point A, not to the left, because that would be point B. So that is what we mean when we say that it's important to include a description of direction when describing vector quantities. Scalar quantities are quantities that does not require direction because it doesn't change the meaning of the quantity. For example, temperature is 40 degrees Celsius. A very good example is distance. You don't have to report the direction that you traveled when calculating for the total distance. So it doesn't matter if you go northward and then to the east and then to the west and then the east again. What you are only interested is the total mileage or the total ground that you were able to cover. How many distance was your car, for example, able to cover, or how far away did you go? That's distance. Mass is also another example of scalar quantities. Here I showed 65 kilogram. So it doesn't change your mass wherever you are or in whichever direction you are. So you don't need to report the direction when describing the mass, for example. The second objective of this video lecture is to define what a resultant is. The resultant is the sum of two or more vectors. This means that when you add two or more vectors, let's say you are adding two displacement or you are adding two forces, the result is the resultant. Another term for the resultant is the net force. So resultant force or net force, or the net rather. If we are dealing with force, net force and resultant force would mean the same. In this illustration, in this example, I wanted to remind you that we use arrows to depict vectors. So here we know that vector A is directed to the or going to the east direction. This displacement is going to the east direction, or the object is going to be displaced to the east by how much? By 40 kilometers. And then afterwards, if we started here, after displacement A, there is a westward displacement B, 20 kilometers to the west. So the longer the arrow, it also suggests that your vector is larger. So here, my 40-kilometer arrow to the east is longer, and half of that is my arrow for vector B, which is 20 kilometers, but to the west. It's very easy to compute for the resultant when we have parallel vectors. What we mean by parallel is if they act along the same axis. So these are parallel vectors because both of them are along the x. When we are dealing with parallel vectors, the arithmetic works. What I mean here is if we connect the tail of the first vector with the head of the second vector, what we get is an illustration of the resultant. How much would be the resultant? It's just a matter of subtracting the two, right? So it's going to be 40 minus 20, and the resultant would be 20 kilometers. As shown in the diagram, the red arrow is to the east. The resultant is 20 kilometers to the east. Here, you are asked to get the resultant force if force A and B are acting in the same direction. A while ago, the forces or the displacement, the vectors, are acting in opposite direction. This time, the parallel vectors are acting in the same direction. So we have a force, we are pushing, let's say, pushing to the right by 40 newtons. Maybe another person is pushing also to the right with the force of 10 newton. So what would be the sum, or what would be the addition? What would be the resultant if force A and force B would be added? So it's just a matter of simple arithmetic or simple addition. So your resultant is going to be 50 newton to the east as well. So those are easy because those are parallel vectors. But this time, we are going to be dealing with two vectors that are in perpendicular angles with each other, meaning to say one of them would be along the x and then the other would be along the y-axis. Okay, so let's say you want to go to point B here and you are starting at point A. What you can do is walk 40 kilometers to the east and then 20 kilometers to the north. But another option is for you to go directly from point A to point B by walking along this path. Okay? We can see that you would get the same effect. You would still get to point B. So what you do here is you added displacement A and then displacement B, but you cannot do simple arithmetic. You cannot do 40 plus 20 or 40 minus 20 because they are not in the same axis. But you want to add them, meaning to say you want to get this resultant. How do we do that? That is the concern of this chapter. How do we deal with vectors, in this case forces? How do we combine the effect of these two forces if they are lying in different axes? Here, this force is to the left, and then here, this force is downwards. What is the combined effect of these two forces? What would be the effect if we add the two forces? What would happen to the object? Where would it go? In other words, we are looking for the resultant. If we connect the tail of the first vector with the head of the second vector, we get this resultant. How do we solve this? By now, it's good if you notice that what we are able to form are right triangles. Right triangles look like this. Remember, they form a 90-degree angle right here in this first example, and then here in the second example. So since they are right angle, the basic concepts in trigonometry can be applied in solving for the resultant. And remember, when we are referring to the resultant, we want to get both the magnitude and direction of the resultant. So in the next video lecture, I will be showing you how to do that. Please answer these concept checks to test your understanding. I will be showing the answer after several seconds. Thank you so much and happy learning.